let's recap that. An O2 group, something I'll be adding to my abbreviated structures you probably should know, could look like this. Somebody recap why this is bad. Maximum charges, missing an octet at the nitrogen. So we can minimize the charge from 3 atoms to 2 atoms by sharing a lone pair from the oxygen to make a pi bond. It still leaves us with charge, and the other possible structure for this does completely minimize charge by violating the octet rule. And some atoms can violate the octet rule. Some atoms can expand beyond 8. Why can't nitrogen? Like phosphorus, for example, nitrogen's big brother, expands all the time. In OChem 2, I'll show my students in 3 weeks, why they can expand phosphorus beyond 8. Too small. Its nucleus is too small. Most of the atom is made up of the electron cloud. Only 5? Then why does it have 8 electrons when it bonds?
Sorry, I was just going to ask, since it has 5 valence electrons, how does that violate its...
So here it's got 5 bonds, which is 10 electrons. Actually, because it has 5 valence electrons is why we can predict a +1 charge. It has 5 valence electrons minus dots plus bonds. No dots, 4 bonds. 5 minus 4 is +1. Phosphorus, Britain, also has 5 valence electrons, and phosphorus can expand. Yeah, its outer shell, the second shell, can only physically fit 8 electrons. In order to get 10 electrons, it'd have to put those extra 2 in the 3s orbital, so it'd have to start occupying a higher energy shell, which is not impossible. It's just like not going to happen. Phosphorus, on the other hand, its 5 valence electrons are in the 3rd shell. So after it fills the 3p, it actually can still utilize the 3d orbitals that exist to put extra electrons. Okay, that was a very specific one, and probably not one that you're going to see, but I love talking about charges and octet rules. So glad we could do that. Do you have other ones you want to?
I just have, they're about like acid base. One, like why and how does a pi bond act as?
Why and how does a pi bond act as a base? Why and how does any set of electrons act as a base? Is that also a fair question?
Yeah.
So let's take, for example, the base hydroxide. And the acid, here's a fun acid. This is pyridinium. It's an organic acid rather than inorganic because it's made up of a hydrocarbon chain. So oxygen can overlap an orbital in which one of its lone pairs is held with the bonding orbital between N and H. Remember, molecular orbital theory is how we predict whether bonds form and whether bonds break. Valence bond theory just helps us draw structures. Molecular orbital theory helps us predict why structures go through the changes they go through. So an orbital holding an electron pair on oxygen overlaps with the sigma star orbital, the anti-bonding orbital that is the NH bond, breaking the NH bond, which allows the electrons to be recaptured just by nitrogen. So bases form bonds to hydrogens, and acids break bonds from hydrogen and keep the electrons. So your question is, why and how does a pi bond act as a base. Well, let's show something a little similar, a little different. Here's hydronium. Here is cyclohexene. All it takes is that the pi orbital, where the pi electrons are, overlaps with the sigma star orbital that is the OH bond. So pi electrons are used to form a bond with H, which in turn breaks a bond so that oxygen can recapture those electrons. And of course, these electrons return to oxygen. Why, of course? Yeah, between the two atoms that have those electrons whizzing around them, oxygen has them more of the time, is more electronegative. So this also reforms water. And one of these carbons gets to use the electrons. The other carbon loses them. So I go from CH and CH to CH and CH2. Well, a CH has a positive charge. CH, CH, CH2, and CH. Notice how the charge has been conserved too. A net positive 1, net positive 1. Charge is just being transferred. A lot of students do try to use electron arrows in blue. Curved arrows, I should say, because this is not an electron arrow, but it's also in blue. This is our reaction arrow. Straight arrow versus curved arrows. A lot of students will try to use curved arrows to show how that charge is moving, to show how the positive charge is being relocated. Positive charges don't really exist in the same way that a negative charge represents an electron pair often. I have to say often because it's not always. A negative charge can be used to represent an electron pair, but a positive charge here is really just showing a lack of electron density. And these arrows show us how electrons are rearranging and how they're moving. So I can't show how a lack of electrons is moving. I have to show how the electrons move, and that will leave in its wake a positive charge. Did that answer your question? Jordan?
So just to clarify, the left arrow is some form of bond breaking, right?
Here,
Pi bond. Yes.
it actually indicates two things at once. One of them is, like you said, the pi bond breaks. What is the other thing that it indicates? A bond forms. CH bond forms.
Because some arrows just signify a bond breaking. How do we know if they might react? Yeah.
This is a good question, and I think it goes back to a question Calvin asked after the Unit 1 test. How do we know whether an arrow shows a bond just breaking, a bond just forming, or both a bond breaking or forming? Can any of you put your finger on the pulse of that? Calvin? Arrows coming from a bond represent bond breaking. Brilliant. Arrows coming from an electron pair is only bond forming. Yeah. An arrow coming from a bond does not have to be only bond breaking. So here is an arrow coming from a bond to an atom that is in that bond. There's the pulse. Sorry, this is also really hard for me to put the pulse on. To put into words. To put the pulse on. I'm going to try. It's wrong to say that only two atoms share a bond. molecular orbital theory clearly proves that there can be a 2-electron, 3-atom centered bond. 3 atoms that share 2 electrons. Molecular orbital theory also says that, like aromatic rings, have some really complex bonding going on. Anyways, when an arrow starts from a bond and points to an atom in that bond. When an arrow starts at a bond and points at one of its 2 atoms. Bond breaking only. When an arrow starts at a lone pair and points at an atom, bond forming only. When an arrow starts at a bond and ends at an atom that's not a part of that bond, bond breaking and bond forming at the same time. I think those are the 3 things that arrows will do. I say I think because I've only been doing this for a few years. 3 things. An arrow starts at a bond and points at one of those 2 atoms, bond breaking. An atom starts at a lone pair and points at an atom, bond forming. An atom starts at a bond and points at a new 3rd atom, bond breaking and bond forming.
Will that one always be for, like, it can't be within the same, like, molecule, can it?
Sure, yeah. We'll talk about that in Unit 3, Unit 4. Intramolecular versus intermolecular reactions. Reactions certainly can exchange electrons within a molecule. Certainly.
And then if there's no
Frequently.
arrows and we're just supposed to figure out how that
Yes.
where
If there's no arrows and you simply see the change, I like to call that a game of spot the difference. What bonds remain unchanged? Don't touch them. What bonds break? Make sure that you have arrows showing those bonds breaking. What bonds form? Make sure that you have arrows showing those bonds forming. And if something is happening at the same time, carbon-carbon pi bond breaks, carbon-hydrogen bond forms, then those arrows are going to overlap. Now I've been noticing I've had students that start OCHEM up at the U and come back down to like transfer back here, and they'll bring their graded mechanisms down from the U, and they'll show some interesting mechanisms that get graded with full points. For instance, this example. How do you, okay, you spot the difference and you recognize that the CH bond breaks, or sorry, the CC bond breaks. So you show the CC bond breaking to one of its atoms. And you notice that a CH bond forms, so you show that carbon attacking a CH bond. And then lastly, an OH bond breaks, so you show the OH bond breaking. They've used 2 arrows to represent something that 1 arrow should be used to represent. I would actually take partial credit off for this because it seems to suggest 2 things. At any given moment, this molecule is taking the electrons and moving it to this carbon and then having that carbon attack, which is different than just saying this carbon takes it to attack.
I took both Gen Chem 1 and Gen Chem 2 at the U, and that's literally what they have us do.
They teach you this. Oh, I don't get it.
Yeah, I don't know.
No, I've never seen that anywhere else other than the TAs up at the U. I know a lot of you guys watch YouTube channels too. Have you seen anything on the OCHEM tutor that would show something like this? Yeah, that's normal and better, more accurate.
On my DET program shows that the difference like the pi bond breaks.
Yeah.
And the electrons have to move to the carbon, and then the carbon lone pairs attach the other atoms.
Which gives the impression of a 2-step thing happening.
Yeah.
First, the bond breaks to a carbon, then the carbon uses them. When analyzing molecular orbital theory, there is not a first then. It's the carbon takes them to use them at once. This is a worksheet I give to my OCHEM 2 class because it's a little too involved. It goes into OCHEM 2 reactions, so I've not decided yet whether to give it to you guys or not. But they have some arrows, and I think this was this might be ophthalmology. Never mind, I thought this maybe was DAT materials, and I wanted to see what they showed, but they don't actually show a lot of mechanisms. Okay, so Jordan, you asked this question, how do I know whether a bond's breaking, whether a bond's forming, or whether a bond is breaking and forming? Did we clear that up?
Yeah, I guess just, I think it was on the first test, and it had to do with like acids and bases as well. You gave us like 2 molecules, and there were no arrows and there were no products.
No.
How the
No. I couldn't have given you both. If that's true, you should send me a screenshot. If I showed you no arrows and no products, there's no way I could. On the part A or part B?
part B.
No. I give you one or the other, and I actually can't remember. It might be that there are options for you to get one or the other.
There was an arrow.
Okay, there was an arrow. One arrow. And maybe the one arrow didn't make sense to you back then? Okay. So one arrow, did it start from a bond or from a lone pair?
It started from
Or a charge?
a charge on oxygen.
And a negative charge would represent a lone pair on an oxygen. And it pointed to an atom, which would suggest bond formation only. Should I show any of the other bonds breaking then? No. Like for instance, in this acid-base reaction, nothing is indicated about this original OH bond, so nothing should change about that original OH bond. Nothing else was indicated about this cyclic nitrogen structure, pyridine, so nothing else should change there. And that's my biggest advice to you is, if you see a small number of arrows, then you should be making a small number of changes. There are very few bonds that should be breaking and forming at any given time. And I see a lot of students that make some pretty creative guesses about what could be happening, but I've actually seen students add arrows on their midterm exam. I'll give them the arrows and ask them to predict what comes after it, and I will see students that add arrows so that they can change the prediction. No, I'm not asking you to figure out what's going on. I'm telling you.
I have a question kind of going with that. a
Okay.
little bit. Sometimes I get confused how you're supposed to know if it's gonna like just form one product, like it's just gonna bond together, or if it's gonna create two. But I guess if you're giving us the arrows or the product, we would be able to see that.
Yes, and if you've seen your practice midterm, I have you do both. You will have a question that asks you to add arrows based on the starting material and products. So spot what bonds break, spot what bonds form, and show the arrows to make that change. And then I have another question that asks you to draw the products based on the arrows shown. And so you have to interpret what those arrows are describing about bond formation and bond breaking.
So like for this one though, this is from our worksheet.
Yep.
How would you know? Well, like why wouldn't this just take like a hydrogen from it?
Well, because I don't see any BH bond breaking.
Okay.
No, that's a valid question. Does my answer seem valid?
Yeah, but draw it out anyway.
Bond formation, yes or no? From a lone pair to an atom, bond formation. Any bond breaking, yes or no? Why not? No arrow starts at a bond. So there is no bond breaking that occurs. So your question is valid. How do I know that this isn't going to give me this, which is I don't like it. That's not a normal molecule. How do I know it's not going to give me this? Because I never indicated that a BH bond was breaking. So why did you break a BH bond? And I didn't indicate that a bond was forming from oxygen to hydrogen. I indicated a bond was forming from oxygen to boron. Yeah?
Is that, like, you will specifically draw to the hydrogen?
Oh, yeah. So this, if I wanted to show you this product, would have to be shown this way. I'd have to show the BH bond breaking and show the O bonding to H. We can't assume what's being broken and what's being formed. We have to explicitly state it. And again, what we're trying to do is detail how chemical changes happen. Not physical changes, but how chemical changes happen. Except for resonance. That's actually not depicting any chemical or physical change. That's just us being kindergartners and trying to represent what molecular orbital theory does a good job summarizing at once in our little pictures. And I say we because I mean us as humans. We have a hard time understanding MO theory, so we use resonance to make sense of it. Resonance does show bond forming and bond breaking, but it's always pi bonds, never sigma bonds. Resonance is only the delocalization, the movement of pi electrons. But this is not a normal reaction. So I don't want you guys to look at that and think that that's a normal thing to see. This actually is quite a normal reaction. Borane is a chemical we'll use in the second half of the semester, and it's only ever used in the presence of an ether, and this is a common, they call it an adduct. This is a common adduct that an ether and borane forms. Okay, so I don't like this. I think it's a misrepresentation. If you've got a contact at the U you want to have come and teach me something, I'll teach them a thing too. I'll try anyways. Again, bond line structure, boy, you know what? After I crossed that out, it looks really confusing why that's wrong. And it's because I hid that double bond. We detailed this, but I'm going to try to see if we can summarize it. If I've got a bond, an arrow that starts at a bond and points at one of those two atoms, bond breaking. If I've got an arrow that starts at a lone pair, and sometimes we actually show this as a negative charge to represent the lone pair. Sometimes. That's bond forming. And I can do the same thing at once, where I show a bond breaking and a bond forming at the same time. Thank you, guys. I've never been able to say it this concisely. Oh, but tell me if it was good. Okay. I'm like, just patting myself on the back. By the way, let's show what some of these products are. This one's hard to say because it doesn't really have a right answer. I don't know whether A or B is taking the electrons until I see it in the next step. But here it's obvious that B has taken the electrons and A has not. You notice that conservation of charge I put into my little A, B's, and C's? A lost electrons, so it became A+. C gained electrons, so it became C-. And B, I almost called it boron, B kept its electrons, so it stayed neutral. Okay. Before we go into any more specific ones, do you have more specific ones?
That kind of actually covered like everything.
Nice. I want to see if we can build more to this list. Are there other questions you guys have from the practice midterm? Calvin?
Question 2, question 6.
2, 6, 13, 15. Well, good, because I wrote 3 anyways. Others? Tanner?
19/nomenclature in general.
Good. More? Vivi?
Can we go over some of the NMR and like AR graphs and stuff?
Yep. And I think 29 and 30 are spectroscopy. Yeah. So those would be good. And then if you have follow-ups to those, let me know. Okay. Questions not from the practice midterm, questions from the active, from old study materials. Britton?
You over the last part, just, no, the second to last part.
You want like part B?
Yeah,
For your,
yeah, on the part B. Okay.
sure, for your question? Or just like in general?
Kind of in general, but I just want to see the final product. Is that idea, right?
Yeah. Let me do that not on the recording. And then I can save those questions longer. I don't. There's, I think, 4 or 5 different structures you could have gotten. Yeah. Did you see my feedback yet, Britton?
Yeah.
I didn't give you the name.
Last time just no.
Sorry. I tried to make sure you knew what the right name was, but I might not have.
Yeah, I missed something because I read it online.
I'll come around and show you for sure. But we can talk about that. What I will say is you will not be graded on solving a problem quite that challenging. I gave you an hour to do that problem. I'm giving you 90 minutes to do the exam. I don't suspect you all took an hour to solve that structure. Some of you, it might have been. Some of you, it might have been quicker. But there will be a bonus question like that on the exam. So if you can even speed race it, you can't lose points on a bonus problem. Speed race it on the exam and try to come up with something, great. But you will not lose points for a problem like that. There were skills, though, in that part B that show up again in the multiple choice questions. Like, can you identify what the integration of this NMR signal represents? Can you identify what functional group is present because of signals in the IR? So we can talk about those skills, and that'll come up with the midterm questions, but I think rather than giving away one of my problems, I'll give you that answer. Layla and then Jordan.
Can you go over, like I had a question on like there's a courses and mass spec and it gave you different molecule choices based on the mass spec thing, and it had either chlorine or bromine on it, and I was just like,
Sure. So if you're seeing a question and it has a lot of bromine and chlorine, it's asking you about isotopic clusters.
yes. And it looked like there were multiple, if that makes sense. Like I guess
Yeah.
my question is like, base peak shows what is the most abundant fragment.
Just the most abundant fragment. That's what the base peak is.
That's the molecular ion.
It's usually not the molecular ion.
Okay, so then how do you find the molecular ion without knowing what the structure is or having any clues?
Two things. The molecular ion is always a radical cation, as opposed to daughter fragments, like the daughter ions, in which the radical has been lost to a fragment and the cation is left over as a smaller part of the molecule. But the molecular ion always has a radical and a cation, either on one atom, because one of its lone electrons has been lost, or shared between 2 atoms that used to be bonded. A pi bond that has now lost 1 electron, or a sigma bond that has now lost 1 electron. So molecular ions, if you're being asked a question like, which of the following is a molecular ion? It needs to have a radical cation. It needs to have both. It cannot have just one. And it needs to have every single atom from the structure. Or if it says which of the following is not a molecular ion, find the odd one out. Find the one that is just a radical or just a cation. If it asks something like, which of the following fragments can form the base peak signal? And if you see the mass spectrum and you know the base peak is not the molecular ion, you would know that because it's not the heaviest mass signal. There is a heavier mass signal and the base peak is not the heaviest mass. Then the base peak is not the molecular ion because it weighs less than some of the other signals. And if it says which of the following gives that signal, first of all, make sure the fragment you're choosing is a cation and not a radical, because radicals don't form signals in mass spec. They're not pulled by the magnetic field. Only ions form signals. With the isotopic clusters, we know it's a bromine isotopic cluster if the ratio is 1 to 1, and we know it's a chlorine isotopic cluster if the ratio is 3 to 1. So just identifying those shapes is usually what those questions are getting at. Allie?
Can I ask a question about those shapes? There was one question on active where I think it was bromine, but it was 1 to 2 to 1. Like there was 3.
Yes.
And I was like, wait, no, I thought.
So we had a similar problem on our worksheet where we had 2 chlorines. And the molecular ion was not a 3 to 1 ratio. But that's because there's now very good odds that both chlorine atoms are 35. Less odds that one is chlorine, one is 35, but because there's 2, it could be either one that's 35 and 37. And then very small odds that they're both 37. But all of those possibilities exist. If it's bromine, what are the odds that both are 79? What are the odds that both are 81? And then what are the odds that one is 79 and one is 81? Well, because these are basically 1 to 1, if I have 2 bromines in my structure, the odds of having one of each is the greatest. So that's, yeah, the 1 to 2 to 1. The odds of having one of each is the greatest. The odds of having 2 79s is less. The odds of having 2 81s is less. I don't get into those multi-cluster or like multi-atom clusters on your exams. Just looking that you can identify those classic isotopic clusters. Jordan.
This will be really quick. Can you go over counting hydrogens for this on aromatic rings? I was like doing the assignments and stuff, and I just am maybe probably overthinking it.
I'm not sure I understand.
Um,
On the NMR.
yes.
So first of all, if you have an aromatic ring in the NMR, where does it show up on our chemical shift? Yeah, like 6 to 8 typically. Not always, usually. And like the signals for alkene hydrogens, vinyl hydrogens, the signal for aero hydrogens is not always nice and clean. It can get a little messy. The splitting patterns are a little messy. So a lot of times there are multiple signals in here, and I will give you the integration of all of them together rather than individually. So you might see 3H, 4H, 5H. First of all, if it was benzene, which is the aromatic ring, there would be just one signal and it'd be a singlet because all of the hydrogens are identical to each other. Now, as soon as I start substituting benzene, I cannot have 6 hydrogens.
Because the one closest to it is different than the one like farthest from it, right?
Well, I can't have 6 hydrogens because one of the 6 carbons has been substituted, so it no longer gives a signal. There's no hydrogen there. So I now have 5. And these two are symmetric, these two are symmetric, and this one is different. So I should expect 3 different signals, but a lot of times you'll find overlap. So it's just too messy to try and interpret. No, not always. In fact, one of the nicest is if it is 1,4 die substituted. Now I have 2 sets of 2. These two are identical and these two are identical. And that's assuming that these R groups are different from each other, so there's no symmetry here. But actually, if the R groups are the same, there's just one signal. If these R groups are different, these two give one signal with one neighbor, these two give one signal with one neighbor. And that shows up as 2 doublets.
So if one of those is different, can you erase one of the R's?
Yep.
On that, let's see, like the fourth carbon, how many neighbors do you say that has?
2.
You count both sides.
Yeah.
All
Even though these two are the same as each other,
that one still has 2 neighbors.
it has 2 neighbors. There are 2 hydrogens.
And then same for all the other ones, they have 2 neighbors except for the second and
Yeah, second and sixth.
yeah.
These have only 1 neighbor. Yeah. But you wouldn't always see that in their splitting patterns because they get really ugly. And actually, in the ring, they can sometimes communicate more than 1 carbon down. Do you remember the splitting pattern is because the nuclei have some sort of communication about their spin states? And that spin state is communicated through carbon-carbon bonds. The aromatic rings can be a little bit more complex. This gets into, we'd need to get into our spectroscopy course to dig into this more, and we're just not going to. Sad. Maybe someday.
Are those hydrogens technically not vanillic hydrogens?
They're not vanillic because vanillic describes being attached to an alkene. And there are no alkenes in the aromatic ring. Can you tell me why? Huh?
I don't know if I'm explaining it the right way, but I think it is.
Say it again.
I said they all have 3 bonds, but they all only have 1 hydrogen. And so even though they're only the 3 pi bonds, I don't know.
Well, the alkene is identified as carbon-carbon double bond,
Yes, but they're like moving.
except when it's carbon-carbon double bond 3 times in a 6-membered ring, in which case they are not alkenes. And you might actually think back to the structure of pyridine that I just drew earlier and say, well, that's not the aromatic ring, so those must be alkenes again. In OChem 2, we start to broaden the definition of the aromatic ring, and we look at why those pi bonds behave differently than alkene pi bonds. So pyridine is classified as an aromatic ring, despite not being a 6-carbon chain. Okay, but what about in this structure? This is quinoline. Does this compound have alkenes, or does it have aromatic rings? Does it have an aromatic ring? Alkenes, because it's not that 3 alternating double bonds. I know.
So I had a question about the naming of the benzene. I was a little confused.
We don't need to name benzene for our class.
I know, but I feel like there was a question where maybe it was on
The PLO, yes.
that might be
And it said name this structure as a,
Well, it named the structure is what it was. It named the structure and then asked you to find something about the structure based on the name, but it didn't give anything about this, or it didn't like show the structure.
oh,
And
you're talking about the spectroscopy PLO.
yeah,
Okay.
and it was a little confusing because you said that was a benzene.
Yeah.
In the other PLO, it says that a benzyl is a aromatic ring with a CH2 or a CH3 or whatever.
Uh-huh.
And then a phenol is an aromatic ring.
Yeah.
But then the naming and like it that was the case with this
Welcome to
one.
IU
Trying
Pack.
to figure out, like, I think it was mass spec, trying to figure out the,
How did you know there's an aromatic ring in it? Yeah?
I don't even remember.
So first of all, we can reference this with a functional group we've talked more about, like the alcohol. The alcohol we know shows up in the suffix of IUPAC nomenclature with OL. Benzene can also show up in the suffix as benzene. We can name things aminobenzene, ethylbenzene, tert-butyl-benzene. But we can also name alcohols in the prefix. So instead of naming something butanol, cyclohexanol, methanol, we can name it as hydroxymethane, hydroxybenzene, hydroxybutane. So a lot of compounds can be indicated both in the suffix or as a substituent, and benzene's substituent name is phenyl.
Okay, so benzene is different than benzil.
Benzene is different than benzyl, where for whatever carbon chain you want to talk about, this position off of the benzene ring is called a benzylic carbon.
Okay, because I think that was where I was getting hung up, because I was seeing different things. Okay.
I forgot to tell you guys that I don't usually take my break during the exam review. So if you want to take your break at any time, you're more than welcome to. I want you to have your blood flowing so you can think well. But I want you guys to get the most out of this time that we can. So I'll just keep going through questions. Drew.
I have a question on the HMR.
Actually, I want to take a step back. Layla, did we answer all of your questions about mass spec? And I think I went to Layla before Jordan's question. Do you remember what yours was?
Mine was just about the aromatic ring counting. I just was
Right.
overthinking the symmetry about it.
And that then got us to this one. All right, Drew.
My question is related to the aromatic ring.
Okay.
On our last day, we have to fill out a worksheet.
Yeah,
For example, a benzene with a electric group.
sure.
I think on the spectrum, they had just a 5H as that group. How come that one is just a 5H and we don't use the 2, 2, and 1?
We could, but actually some of those signals overlap. So if you were to manually go into the computer, I have to apologize because I'm in charge of the OCHEM labs. You guys might notice that on the schedule, you were not supposed to do the packet today. You were supposed to do the packet after spring break. Today, you were actually supposed to be in there working with the instruments and taking data from the instruments. But I screwed up and I don't have it ready. And I could have tried to get it ready over the weekend and given you something that hadn't been fully vetted, but I've done that and it's not always a good experience. So I had your instructors flip the weeks, which actually is something to say. I know some of you have lab on Thursday. You might want to take a look at that packet that you're going to do on Thursday before our exam Wednesday, because it can be useful in helping you solidify some of your understanding of spectroscopy. And if has your Thursday lab instructor posted the lab for Thursday? Okay, so you have access to it. There's a video, is that right? You guys had a video of me that you can watch me go through the background on the packet and solve one of the problems on each of them. And there's a whole background document, and there's the world of the internet. So it's a really good resource if you feel like you're struggling with spectroscopy. Do your lab early before the midterm. It might answer some questions. So Drew, your question of why aren't we showing this as 221 is super valid. If I went into the computer, which is what you guys would have been doing today instead, and had taken this data, then I could have actually gone in and said, this signal here has an integration of 2H, and this signal here has an integration of 3H, and now you might be thinking, well, which 2H is this, and how do I get 3 H's that are all identical? They're not all identical, right? There is a 2H and a 1H overlapping, I just can't tell. And I honestly am not confident that this 2H is its own 2H hydrogen and not just some weird overlap of all of this. And sometimes it's not even as clear as having nice distinct signals. It's really just a big spread of peaks. So by integrating the whole region, I'm really not interested in the symmetry of the 2 to 1. I'm glad that you guys recognize it, but I don't care much because 5H tells me one thing comes off the ring. 4H tells me two things come off the ring. 3H tells me three things come off the ring. So it helps me predict how many hydrogens are on my ring and how many groups are on my ring. There is one case where the shape of the signal can be useful. If I have a 4H that looks a little bit like this, a little messy, it's probably two groups that come off of the ring in one of these two ways. But if I have a nice clean doublet and it's very symmetric, then my two groups probably come off the ring symmetric. That to me though that's even too much in the weeds. To understand the difference between this 4H in the aromatic ring and this 4H in the aromatic ring, it's looking at too fine of the details, so I don't get into that too often. All right, I think it's time we go through some of these practice test questions. Christine gave us this one at the beginning of class. This is not usually how my exam reviews go. I usually make a real big list and then we just tackle them one by one. But you know what? I think we've answered a lot of questions, right? 29. So Christine, we've talked a lot about NMR since you brought up this question. So let's approach it with some of the insight that we've gotten. Which compound belongs to the NMR spectrum shown? There's a lot of things that I can start by analyzing. One is actually a mistake that I had on a number of your part Bs. I put the wrong integration. I think that happened on yours, Britton. I put the wrong integration on one of the signals, which meant the total number of hydrogens on the NMR spectrum added up to 8. And the chemical formula was reported as 10 hydrogens. All of the hydrogens in a sample give a signal in a hydrogen NMR. So how can the number of hydrogens by integration be different than the number of hydrogens in the chemical formula? I made a mistake. That's how. So first of all, you have to trust that I didn't do that on the exam. And I really thought I updated that question, which is why I was so upset to see that that became a roadblock to some of you solving that question more easily, because I really thought I had fixed that. First, you have to trust that these are actually the signals. Actually, I think in the spectroscopy PLO, one of the questions is, how do you know the chemical formula has 12 hydrogens? And there's one signal on the spectroscopy PLO, which I did not make, that doesn't have its integration listed. And so that question, how do you know there are 12 hydrogens? I've had a student that said, I didn't know that. It adds up to 6. So that's news to me. The only thing you could say is, based on the way this question is worded, I can only assume that the missing signal has an integration of 6. So assuming all of the signals are labeled and their integrations are correct, well, I can look at the number of hydrogens and then compare that to the number of hydrogens in my compounds. 4, 5, 6, 9. I should have 9 hydrogens in my compound. Then I look at these and I count up the hydrogens. it's a little bit tedious. So is there something we can do to rule out structures faster? I can use the chemical shift to try and predict the functional groups. So many of you, I assigned 1 point to describe how the NMR in your Part B helps predict functional groups. So many of you gave the generic answer. You said, the chemical shift helps because it shows you how the hydrogen signal appears along the x-axis, and that's the functional group. Right, but in your sample, it usually doesn't help at all. There's a few functional groups. Carboxylic acids and aldehydes, although they show up in the same region, so if you saw a signal there, you would need IR to confirm whether it's aldehyde or carboxylic acid. Aromatic rings, although sometimes alkene hydrogens show up in the aromatic region. Alkenes, although sometimes functional group adjacent compounds that are compounded by multiple functional groups show up in the alkene region. So how does your NMR help predict functional groups? Well, in this one, it sure looks like I've got aromatic hydrogens. And then it looks like I've got an alkene. But I don't have a sample, I don't have an answer that has both aromatic hydrogens and alkene hydrogens. I have some that have aromatic and some that have alkene, but not both. So maybe this signal is not actually in the alkene region like our correlation table predicts. Maybe it's in the functional group adjacent region twice. And then it looks like I've got something functional group adjacent, and then it looks like I've got a methyl. Okay, so I can look for things with aromatic rings. That narrows me down to B and D. Although if you're not confident in that, that's okay. Don't rule out C then, because C has alkenes, and sometimes alkenes shift into the aromatic region. Sorry, and I'm talking to everybody, but this is Christine's question. Then I can look for groups that have CH3s. Oh man, every single one of them has a CH3. So the CH3 actually isn't helpful. Oh, but the CH3 is a singlet, which means it has no predicted neighbors. Well, that would say this one, but B doesn't agree with everything else. B should have 5 aromatic hydrogens. And did I do my math wrong earlier when I said 9? No, I did 9? Okay. Oh, sorry, I'm doing my math wrong here. Here's 5 and 3, which is 8. So B doesn't agree with the total integration. A lot of things wrong with it. Okay, so I want 4 hydrogens, a group of 1, a group of 1, a group of 3. Here's my 4 hydrogens on the aromatic ring. Where's my group of 1, group of 1, group of 3? Britton?
Yeah, the one on the alcohol.
The one on the alcohol.
One on the
Secondary carbon. And the methyl group. That secondary carbon looks like it has 3 neighbors, so it should show up as a quartet, but I really don't see a quartet. And the methyl group has 1 neighbor, so it should be a doublet, but I don't really see a doublet. Isn't that the hardest part about experimental data? You don't always get what you'd hope to expect. I know. Okay, so how about this? I've got the 1H from the alcohol and the 1H from the secondary carbon. Which hydrogen produces which signal? Does the 1H from the secondary carbon show up at 3 or at 4.5? Closer to that oxygen, that signal is going to shift left.
So the one by the 5 would be the one attached to the oxygen.
Plus, that hydrogen, it's not just adjacent to the oxygen, which would shift it close to 4, but not usually past 4. It's also adjacent to the aromatic ring. It's functional group adjacent twice. So it gets compounded and its signal shifts even further than you might expect. That signal at 4.5, that looks like the alkene region. It's because it's compounded by 2 functional groups. And, oh, sorry, there's more to that. It's a shorter, broader 1H signal, which might suggest that it is splitting into a quartet that we just can't see. The other 1H, it's not just adjacent to an electronegative atom, it's attached to an electronegative atom. Why isn't that the furthest to the left? Because oxygen is weird. It can hydrogen bond, it can re-shield its hydrogen, its signal shows up anywhere from 0 to 5. It's not always the furthest left, but it doesn't split. The hydrogen attached to the oxygen, always a singlet. And so I've got 2 1H signals of different heights. One is a clean singlet, taller, skinnier. One is actually split, shorter and wider, explaining why they have different heights. Jordan?
In my notes I have written down that hydrogens on OH or NH. Is that what you were saying there? They never count for?
Yes, the hydrogens on alcohols, the hydrogens on amines.
Not amines, right? Just amines?
Do you know what? I don't have this on your correlation table, and I don't think I've ever used a question. I've never analyzed amides. I think that might be what it is. I think amide hydrogens actually show up close to carboxylic acids, but I never report it. You got a good point there. I've changed my IR correlation tables to say amine-amide because they behave similarly. I think amides, though, are in the 9 to 12 region. I don't have a good answer on that.
So by saying they don't count, does that mean obviously not in the total because we're counting that oxygen is bonded to that? Like in
They count in the integration. They don't count as N
for
neighbors, and they don't have neighbors. Loners. Christine, did that help answer your approach? I think I went through it too much and I didn't have you analyze it enough. Vivi, and then Kirsten. That's right. So OH is always a singlet 1H. Unless, of course, there's symmetric OHs, in which case then it's 2H, 3H. Sorry.
My question was just the other half of that. I understood that it's always going to be a singlet, but you said they don't count. So if there was like looking at
Yeah,
that,
like this 1H on the carbon,
H doesn't have,
it has 3 neighbors on the right,
so it would.
and that's it.
Okay.
It doesn't have 3 neighbors plus 1 neighbor for a total of 4. Yeah. All right, let's try number 30, and this time, Christine, do you want to try and walk me through your question here, which I think is where I should have started on the last one.
Well, it's probably because I don't know which one is the tertiary carbon.
Oh, what does tertiary mean? Is that the question? The roadblock is
Another question that I got wrong, which is I think number 7.
on substitution.
It says what's the best descriptor for the carbon labeled atom 1?
Yeah. That's what we call carbon substitution. Earlier, Christine, on question 29, you might have heard me say secondary carbon, in which I was referring to the secondary alcohol carbon. This is a secondary carbon because it's bonded to 2 carbons. So we describe carbons as methyls if they're bonded to no other carbons, primary, secondary, tertiary, and quaternary. And these can describe functional group carbons too, not just alkane carbons, which is why you can have methyl alcohol, primary alcohol, in this case, secondary alcohol. But you can't have a quaternary functional group. Why can't I have a quaternary alcohol? It has to be bonded to 4 carbons. So to also then be bonded to an alcohol, ooh, it's gross, right? It's okay. It doesn't have feelings. I actually don't know that that's true. That's a topic for another day. So, question 30, can you identify the tertiary carbon? Right. 3 other carbons. Yep. There's actually only one other degree of substitution. In the whole molecule, there's 2 degrees of substitution. There's a tertiary carbon, and there are 3 primary carbons. Bonded to 1 carbon, bonded to 1 carbon, but that's bonded to a carbon and an oxygen. It's not what it's based on, right? It's based on how many carbons it's bonded to. Primary alcohol. So we can describe that the oxygen is there, but we don't describe that in its substitution term. Primary alcohol. Okay, so now that we've identified that, can we predict what the integration of that tertiary carbon's hydrogen, can we predict what the integration for that signal should be? In other words, how many hydrogens attached to that carbon? What integration will that signal give?
It's only attached to 1 hydrogen, and then it has 7 neighbors?
I think 8. 3, 6, 8. So n equals 8. The number of peaks should be 9. So a 1H signal with 9 peaks. What signal does that agree with? Right. Tanner, you had question 2? Calvin. Thank you. Oh, and I always make this mistake. I will be printing off your exam tonight to check for the typos. No, but sometimes I pick a molecule and then I have last semester's molecule name in the question. Question 2, how many lone pairs of electrons are assumed in the bond line structure? What do you think?
I thought it was 8.
Ah, okay. Can you tell me where they are?
2 on each oxygen and 2 on.
Oh. But nitrogen and oxygen are not in the same family. They're neighbors, not siblings. So I would not expect nitrogen and oxygen to have the same preferred bonding pattern. Carbon, no lone pairs. Nitrogen, oxygen, 2 lone pairs. Nitrogen, right in the middle. So the issue here is that nitrogen will break its octet if it has 2 lone pairs. Nitrogen explicitly has 1 bond, 2 electrons, has implicitly 2 bonds, so that's 2, 4, 6. To get to 8, it only needs 2 more electrons. That's 1 lone pair. I have had students approach me and say, I was trying to count the number of electrons, not the number of pairs. But the wording is important, which is why I bold pairs. So was it do you think it was a matter of thinking of it as electrons? because then you're underestimating the oxygens. The oxygens need 4 additional electrons to get up to their octet. So they do have 2 lone pairs, but the nitrogen has 1. I do a little bit of psychology when I write these questions. Like 5 is an answer, or no, 4 is an answer because there are 4 atoms that have lone pairs. So I'm looking for that student that is thinking how many atoms have lone pairs on them. 4 atoms have lone pairs on them. And looking to check your understanding that you can count the number of lone pairs. I want you to do that because when you leave and stop being chemists, when you get out of my class, I want you to bring that with and teach the people that you work with. Tell them how to look for lone pairs in their molecules, because we assume them, and you know what happens when we assume. Okay, good. And you also had 6. Which of the labeled groups is predicted to have the lowest pKa, the most acidic? What trend can we use to rank acidity? What acronym can we use? Cario. What does C stand for? Charge. Typically, more acidic is more positive. More basic is more negative. Especially if all else is the same, you can rank by charge. What is A? Oh, I should have said, does charge apply across groups 1, 2, 3, and 4? No, they all have the same charge. A stands for atom, and atom has 2 parts. Electronegativity in the same row, and size in the same family. Does atom play a role here? What atoms am I telling apart? Group 1 considers the acidity of what atom? Carbon. Group 2, oxygen. Group 3, nitrogen. Group 4, so I'm considering 3 atoms here. Carbon, nitrogen, and oxygen, which are all in the same family. Sorry, I do this, that's not a family. All in the same row, which means I can rank their acidity by electronegativity. Who's the least acidic of that family? Carbon, then nitrogen, then oxygen. So I've really narrowed it down to groups 2 and 4. And dang, that's an answer. Groups 2 and 4 could be a possibility according to your instructor. So now I need to rule out, is it group 4 or is it groups 2 and 4? What's different between groups 2 and group 4? Not their charge, so let's keep going. What does R stand for? Resonance. What about I? Induction, which is a push and pull of electrons. And O? Orbital. For right now, I know a lot of you will look at group 4 and call it sp3 hybridized. In OChem 2, we'll actually learn more about resonance and show that atom 4 is sp2 hybridized. If it can engage in resonance, it will engage in resonance. And to engage in resonance, it has to have a p orbital. So it can't be sp3. Carbon 4 loses an electron, or sorry, loses a proton. Carbon 4, I'm sorry. Group 4 loses a proton, takes on a negative charge. That's its conjugate base. And I create a 3-atom system, charge, pi bond. That's a resonance stabilized system. In fact, the carboxylic acid was a group we reviewed during our acid-base section because it's so useful for its acidity. Well, it's called a carboxylic acid. So we still have to rank two atoms that have the same, two groups that have the same atom acting as the acid, but one that has no possible resonance in its conjugate base, and one that does have resonance in its conjugate base. Which will be more acidic? Or are they equal? Resonance always stabilizes. So the conjugate base with resonance is more stable. The more stable conjugate base is less likely to reverse itself and become the acid, which means the more stable conjugate base comes from the more acidic atom. But a cheat code here is to name the functional groups. We didn't have functional groups when we did this learning in Unit 1. I didn't call that an alcohol and call that a carboxylic acid, but now that you know it's called a carboxylic acid, there's good reason to suspect it's the most acidic. What do you think, Calvin? Anybody else follow-ups on that one?
Wait, can you explain why the alcohol doesn't have resonance?
Yes. To have resonance, you need to have the capacity for pi bonding. So on the carboxylic acid conjugate base, negative charge, adjacent to a pi bond, directly bonded to a pi bond. CO pi bond, a 3-atom system, including a charge and a pi bond, that is a great setup for resonance. But the alcohol is connected to an sp3 hybridized carbon. Can't have any resonance. No capacity for resonance because there's no p orbitals nearby directly attached. Okay, question 15. This one was you?
Yes. No.
Still yours. Okay, well, and this was the most talked about question last semester. They hated me for this one. I thought it was good. If you look at these regions, you should recognize, oops, this is alkane region, 0.5 to 2. This is functional group adjacent and a little bit of the alkene, 2 to 5. This is aromatic, 6.5 to 8.5, and this is aldehyde and carboxylic acid. And this is asking the most signals. Most of my students in the fall thought I was asking for the highest integration. So they were looking at carboxylic acid. These two carbons attached to the alcohol and attached to the amine, those will show up in the functional group adjacent range, 2 to 5. My methyl group will show up alkane, and then the OH and the NH2 are likely to show up probably 2 to 5. Oh, well, what did the answer say? Yeah, that's a tough one. That'll make your heart race, huh? It made my heart race a little bit. And I admit I don't always ask the best questions, so I'm always revising and reiterating. I liked the route that this question was on. I don't think it was asked very well, especially since it didn't line up with the correlation tables exactly. So you won't see that question again, ever. Okay, now question 19, nomenclature. This should remind you of your Unit 2, Part B, where you were given a compound, you had to draw it, and you were asked to correct its name as well. I love these questions. They let me assess your ability to draw based on the name. Even if it's right or wrong, you can interpret IUPAC wording. And then it allows me to have you take a structure that you've drawn, whether it's right or not, I will grade you on the structure you drew. Well, I mean, I do give or take, I guess. I've had students that draw a structure completely wrong, and then actually correct the name for the structure for what it should have been. But it does not agree with the structure they just drew. So I kind of averaged the points between those two issues. What's your question on this, Tanner?
Okay, so like I understand this question, but I need the rules again.
Yeah, good.
Feedback rules.
So I wonder if we can draw from the audience on this one. What do you guys remember as the rules for IUPAC nomenclature? The audience, sorry. The class. Like I'm in my own little show up here. Sure. I mean, what do you think? What do you use? Okay, so you like this acronym. It's not really rules, but it's a way of thinking of it, right? We don't necessarily have to put this in any specific order. Maybe we can do bullet points. What are some of the rules? Good. Parent chain equals longest carbon chain. And we will revisit this in the second half of this semester to remind ourselves of the caveat that that includes the highest priority functional group. But on the midterm, you will only be naming alkyl and halo substituents. You won't be naming alkenes and alcohols. You'll just be naming alkyl groups and halogen groups. In the second half of the semester, you'll name alkenes, alkynes, and alcohols. So we'll revisit that this should be the longest carbon chain with the highest priority functional group, but right now it's just the longest carbon chain. What else?
I like to number it.
And do you number it more than one way?
I just find whichever one has the lowest.
So number to provide the lowest locant set. That's a good rule. Number for the lowest locant set. Tanner, do you know what a lowest locant set is?
The way you number the carbons.
Good. It's the locant set is the list of where the substituents are. So the locants are how you number it, but the locant set is just the list of where all your substituents are. We want the lowest locant set at the first point of difference, prioritizing the highest priority functional group. But for right now, you only need to name alkyl and halogens. What has higher priority? Equal priority. Alkyl groups are equal to halogen groups in priority. Good. Because I think on the unit test, I had one or two people that said the person did not prioritize the halogen. Don't need to prioritize the halogen. Now, what happens in a locant set that is equal in more than one direction? A tie goes alphabetically. And that's useful as a reminder that the name is listed alphabetically. Did I talk to you guys about why the alphabet is called what it is? The alpha, alpha, beta, A, B, C's. Literally A, B, C's is the same as alphabet because alphabet is just the first two letters. A, B, C's is just the first three letters. So if you turned A, B, C's into like a word, that could one day be the word we use for alphabet, the ABCs. And in Arabic, the first two letters are alif, ba. Alphabet, alif, ba. They're all the same. They're all the same language. Jordan?
There are some parts in the name that don't fit in alphabetically, where they don't count alphabetically, right?
Yes.
Can you remind us what those are?
So not the T in tert butyl. Instead, we go by B. I don't know if that's clear enough. I don't really have you guys use the sec group, but there's a sec butyl as well. Tert here stands for tertiary. Sec stands for secondary. I just don't use the sec butyl group a lot, but that goes for sec. But the I in isopropyl, and of course there is also an isobutyl, but I don't use isobutyl very often either.
So isopropyl does go alphabetically with tert.
And you'll notice tert butyl technically has to have that dash between tert and butyl. It's not one word. Tert is a description of butyl. It's not N-butyl. It's not S-butyl. It's T-butyl. But isopropyl is isopropyl. It's a made-up name.
The other number of words like di or tri or whatever else there is, like the dimethyl, for example, that doesn't count alphabetically technically either, right?
Good. So how do we add that in there? Not D in dimethyl. I feel like IUPAC nomenclature is really easy. It makes a lot of sense. And then I try to write down all the rules. And it's like A subheading I, subheading 1, subheading little a, subheading I. It's like in the event that this happens, in case that happens also, there's a caveat for every rule. Which actually was a good reminder about multipliers. When you have the same substituent more than once, you just list it one time in the prefix with multipliers. It's also a good reminder that every substituent, no matter how many times it's a multiple of the same substituent, every substituent has a locant, even if that's on the same carbon. So a good example might be can you name it? 1,1-dibromo cyclohexane. It feels redundant, and people would like to say 1-dibromo, but how do I know you didn't screw up? And you were supposed to say 1,2-dibromo, 1,3-dibromo, 1,4-dibromo. How do I know that your 1-dibromo is really 1,1? So we lean into that redundancy. 1,1-dibromo.
What if you just say dibromo without the one?
Even worse. Dibromo is worse. But do you know what they do? How would you name this compound? Here we don't need any locant.
But you could add it, right?
You could, but a lot of people don't. Yeah, I wouldn't take off points if you did. But many people won't name this with 1-bromo because there's only one group, so it doesn't matter where it is on the ring.
If you're not naming a locant for the dibromo, then that's kind of, you're saying that that's kind of doing the same thing, like you need the redundancy. And if you don't, then it's like, oh, well, but are they on the same one? Or
This
just makes it
This can't be anything else. If you called this 3-bromocyclohexane, people would laugh because that doesn't make any sense. Calling it 1-bromocyclohexane, people are like, wow, good job. She can count to 1. Here, if you call it dibromocyclohexane, most people will probably think of 1,2-dibromo because in organic chemistry, that's a more common example of a chemical reaction in chemical reactions. 1,1 is not so common. Okay, so how about this? What's the best name here? 1-bromobutane. Why am I now expecting you to put the 1 back in? Right. This is not a ring anymore. So there's not just an arbitrary place I can start. I'm either on the end of the chain or I'm in the middle of the chain. And I have to be able to distinguish between the two. Although some people might use this as like N-bromobutane, N for normal, meaning a straight chain rather than branched, but 1-bromobutane, we have to list the locant because there's not just anywhere I can start, like on the ring. I have to be on one of these carbons somewhere. I need to describe which of them. Anything else we should add to this list? Parent chain, lowest locant set, tie goes alphabetically. List substituents in alphabetical order. List every substituent. List every locant. Britton. Yeah. We'll come back to the priorities after spring break. On your midterm, you don't have to worry about priorities. And when you come back for OCHEM 2, we'll add more groups to the priorities.
So on this exam,
Just on this exam, alkyls and halo groups. And those are equal in priority. Neither takes higher preference, so you just go for the lowest locant set. After that, things change, and you get the parent chain with the highest priority functional group, alcohol over alkene and alkyne, carboxylic acid over ketone and aldehyde, and you go for the lowest locant set, prioritizing the highest priority group. Yeah. Tanner.
Is there good like practice material for this?
Mm-hmm.
Some worksheets?
Yeah, actually, I think Active will have a number of worksheets, or a number of problems for you. Oops, that's the wrong class. Do you remember the practice tab on Active?
I was looking through it, and it was kind of like not organized into like nomenclature. They were just spread out, so I was picking and choosing.
You're right.
But I was just seeing if there's like.
I actually don't have. Actually, I might on the modules. I worry though that it's not just alkyl and halo groups, and that anywhere you're going to do practice, you might run into some other ones. Under this organic chemistry resources, which is actually not my material, I thought there was a nomenclature one here. Appendix of useful materials. Well, that's just a link to the online free textbook that talks about some. In my old 2310 materials, again, these are going to be kind of spread out. And I used to organize the nomenclature introduction differently. I would do strictly alkanes, no alkyl halides, until alcohols were introduced, and then alkyl halides and alcohols combined. So, no, I don't think I have any good practice problems on just alkyl and halo groups. But if you go to that review session tomorrow, whether or not there's a tutor, then you and your classmates can brainstorm, draw out structures, and then have each other name them. I would say try to use AI and say, can you, but AI sucks at organic molecules. Vivi? The organic chemistry tutor, nomenclature. And how about the one that we did on nomenclature? Did you do all of these?
Yes, but I was like, not confident. Like, is there a key for this?
No, just what we did in class. I will say you can always send me your work and I'd be happy to review it and give you feedback on it. But I am really bad at making keys for these worksheets, especially since I'm not confident that I'm going to keep them the way they are. Anybody else suggestions on nomenclature practice? I think the organic chemistry tutor nomenclature video is probably a good resource. Oh, I TA'd for a professor at CU Boulder one summer who had a huge document. There is another resource I recommend to you guys in the external resources page, and it's organic chemistry as a second language. I feel pretty confident that he has a number of nomenclature problems, but I mean, it's a little down to the wire in terms of getting it. Oh, I've got a copy that you could swing by and take some pictures of or borrow. Okay. Feel good?
Yes.
I think I would say take this list of rules and go back to that worksheet and see if the names you came up with really did work. Oh, here's another resource. On the midterm module, you all have access now to all unit test questions. I told you about this last week in the email. Has anybody taken advantage of it yet? It's only been active for like 12 hours. So you got a question like whatever the midterm had on your Unit 2 Part B, but there were maybe 2 other problems like that as well, 2 or 3. So you could go through these and try to find that same problem, but the other versions of it. And then you'd get more practice on exactly the same thing. Draw it, rename it, identify the error. But there's no keys, because there's no answer to it. Sorry.
Still good. Thank you.
More practice. Yeah. Allie.
I felt like on the practice midterm exam, there wasn't any questions about like chirality.
Sure.
Like, I mean,
Yeah.
like configurations of things. Like I'm assuming that's
Yeah.
on the exam.
Okay, so I think some of you got this on the unit test. There are some absolute configuration questions I can ask that it says, is the absolute configuration R, S, neither, because it's not chiral, or no way to know, not enough information, because it's chiral, but it doesn't have a wedge or a dash. Those are really kind of tricky. I don't like to throw those onto the exam. I find that determining absolute configuration on an exam takes a lot of time. So I don't always throw them on there. If I do, it's often a bonus question. Assign the absolute configuration to the structure that's already shown. But or draw the R configuration of this chiral center. But there's always at least one question on, is the molecule chiral, achiral, meso? What's the relationship? Enantiomers, diastereomers, structural isomers, identical? And they will come back up in the second half of the semester, but you're right, I don't ask a lot of questions on them.
I was like, I'm not drawing like so many little arrows or anything.
I know.
Am I missing something?
I just feel like it takes a lot of time, and I don't always put those on because of that. Yeah. Mm-hmm.
This is not really related at all. But in chairs, up and down are like
The two relative positions.
wedged and dashed.
Yeah.
If you're looking at it.
Yeah, if you've got a top-down view of a ring, you've got groups that are up towards you and down away from you, wedged and dashed. And when you look at the side-on view, the chair, those groups are up and up, or down and down. And anything that's up will flip between axial and equatorial up. And anything that's down flips between up and equatorial, down and axial and equatorial.
Yes.
Yeah.
I feel like we talked about, this is going way back, MO diagrams a little bit, but then I feel like there was
Not a lot on it.
yeah, all we asked was for the hydrogen MO diagram. Was that
On the unit test?
Yeah, understand like orbitals more?
Just to recognize it. Oh yeah, so MO theory will be the foundation for why chemistry happens. But it is hard to represent, and it takes up a lot of space, and it is really complicated, so I'm not going to dive into it deep. But I want you guys to realize that this is a lie. Nothing behaves like this. MO theory is so much more complicated than that, and it does a better job of predicting chemical behavior than, you know, like we showed earlier how an alkene can be a base, creates a carbon cation. Why? How? We'll actually talk about that after spring break, and we'll use MO theory again. So I want you guys to have a baseline for what MO theory is. It comes in well in Unit 1. But on your midterm, you might see a question on it. It's not very common. And it's usually more, it's less of an image and more of a worded question. Like, what does MO theory predict would be this? I think with MO theory, if you see a question on it on your exam, don't overthink it. It's probably as straightforward as it seems, because that's what I try to get at. Thank you guys. That went fast. It's like faster than normal. Send me any last minute questions you've got before our test Wednesday night. Where do we meet? Here. What time? 5. And we'll get started around 5:10 or 5:15. So those of you that might come in a little late, we'll just do a little bit more question review. Good night.
If you guys are community and prompt workshop tonight, it's at SI 137, which is just in the tutoring center.
Okay.
It's like the room in the bottom floor, like in the corner.
So if you want to go to tonight's impromptu tutoring session, first floor in the corner. And if you want to go to tomorrow's tutoring session, put your tutoring hat on.
Yeah, it might be canceled.
I'll try to update you if I get any news.